Good morning, everyone. Am I audible?
Yes, sir.
My screen is visible or not? My screen visible?
Yes, sir.
Okay. So let's begin. Yesterday at the end, I stated a theorem. 1 minute. So let us recall that theorem again and we will prove it. So what we were discussing is, so we had a convex set, okay, which is complete, and we have a point outside that convex set, and we were looking for the distance from the point to the set, and we asked an existence and uniqueness result. Okay, so it is existence and uniqueness problem. So let's see whether that is true or not via this theorem. Let X be an inner productive space and M is non-empty, convex subset, convex and complete subset of X. Okay, then the conclusion is, for given any point X in any vector X in this inner productive space capital X, there is a unique vector Y in the subset M such that this distance, so this delta denotes the distance. Okay, I'm writing distance of M from X. Okay, and by definition this is infimum over all infimum of norm of X minus Y, where Y runs in M. And our claim is okay. So let me write it in this way. So let me write it Z, because this Y and this Y you may get confused. So let us write Z here. Okay. So let's see its proof. Oh. So we will use the definition of infimum. Okay. So from the definition of infimum, what we get a sequence Zn. So sequence, this sequence will be in M. Okay, and such that this delta n, we define delta n like this: infimum over okay, don't write infimum, it's nothing but X minus Zn. it converges to delta. Okay, so what is happening here? Say we have this M. Okay, so here it's not convex, make it convex here. So suppose this is convex and we have a point x somewhere here, and suppose this is the infimum. Okay, and we have to prove that this point y belongs to M. So here what we did, we took elements from, so Zn's from M, so they will convert somewhere here. So here we are taking these distances, this delta n, these are delta n's. So this distance, say this is z1, if this is z1, z2 and so on, say zn. So this first one is, this distance is delta 1, second distance is delta 2, delta 3, so this is delta n, and the last one is delta. Do you get this? Hello?
Yes, sir.
Okay. So this is how we are getting this sequence. Okay. So what we prove, we will prove that Zn is Cauchy. Is Cauchy sequence. This is our claim. So what we do after proving Zn is Cauchy, so you know this set M is it's complete. It is given here. This set is complete. Okay, and you know by definition of complete complete normed space or complete metric space, if the Cauchy sequence is convergent in a complete metric space. Okay, this is the definition. So you will get that this Zn is convergent, and then you will show that in fact it converges to y. Okay. Now we define another vector. So you all know here that these Zn's are elements of M, and M is a subset of X, means Zn's are vectors in X, and X is also a vector in X. This means X minus Zn is a vector in X. Correct? Call this vector Vn. So define Vn equal to X minus Zn. Okay, this is a let's do it other way, Zn minus X. Okay, so from here we will get, since delta n is this thing, so we can write norm Vn equal to delta n. Okay, any doubt? Now
Now
we will use
we will
parallelogram
use
law.
parallelogram.
So for that, first consider Vn plus Vm. So it will be Zn minus X plus Zm minus X, which is Zn plus Zm minus 2x. Correct? So
Now
bring 2
bring two
out,
out,
you will get
you
norm
get
so norm of 1 by
so
2
norm of 1 by 2.
Zn plus Zm minus X. Okay?
Yes, sir.
Huh. Okay, now we also know that M is convex. Okay, M is convex. It is given that M is convex. So for a convex subset, if two elements are there, so Zn and Zm both belong to M. Zn belongs to M and Zm belongs to M. Correct? So by definition of convexity, 1 by 2 Zn plus 1 by 2 Zm, this again belongs to M. This is, how do you see this? So, here is our Zn, Z1, here is our Zn. So if you draw this vector Zn minus Z, okay, so what is that, this point U? 1 by 2 Zn plus Zm, it is somewhere here, okay. So this is by definition of convexity. So how do you define convexity? You say if two elements x comma y belongs to M, then for any lambda between 0 comma 1, this happens, lambda x plus 1 minus lambda y belong to M. Here your lambda is 1 by 2. Okay, here lambda is 1 by 2. Do you see this point? If M is convex, so this part, this vector belongs to M. And here you have, okay, let me, so Vn plus Vm, we have this thing, and then for parallelogram law, we also need Vn minus Vm. So what is Vn minus Vm? Vn minus Vm is Yn minus, so we are taking Zn's. Zn minus x minus Zm minus x, so minus minus plus, okay. So this will get cancelled, so we will get Zn minus Zm. Okay, now let us consider I'm writing y, Zn minus Zm square is same as Vn minus Vm square. If you remember parallelogram law, so this will be 2 of from Vn square plus Vm square minus from Vn plus Vm square. Correct? Any doubt? Okay.
Okay.
But Vn
But
square
Vn
square
square
delta n square, V is delta m square, okay, and uh, yeah, and use norm Vn plus Vm is less than equal to norm Vn plus norm Vm. Use this thing, okay. So what you get is, from here what you get is, this is less than equal to, use this, what you get is, first this is less than delta n square, this is less than delta m square, so delta n square plus delta m square. Now you see here it is negative sign, here it is negative, okay, so it will be 1 minute, wait for a minute. Okay, so this will be minus of 2 delta and 2 delta. So here we do one thing. We will not use this. What we will use, we will not use this, but what we use is the definition of delta. See, the delta is infimum infimum of this norm x minus z. Okay, so Vn plus Vm, we have already seen here. Now Vn plus Vm is 2 times norm of 1 by 2, and so this is an element of capital M minus x. So this is always uh, greater than equal to 2 times delta. Vn plus Vm is always greater than equal to 2 times delta. When we square it, it will be 2 delta square. Correct? Any doubt?
सर ये टू डेल्टा सर ये कैसे, ये एक बार फिर बता दीजिए कैसे सर आपने ले लिया? ये
ये
तो समझ में आ गया,
2
हाफ जेड एन
2
और प्लस जेड एम का एलिमेंट है।
हाँ, ये 2 था,
हम्म।
ये 2 यहाँ पर
यस
आया।
सर।
अब जब मैं इसका
हाँ।
स्क्वायर करूंगा तो ये पूरे का स्क्वायर हो जाएगा,
हम्म। टू डेल्टा
है ना?
सर, इसको आप डेल्टा लेट कर लिए हैं?
नहीं, लेट नहीं की मैंने, ऐसा नहीं। मैं अगर डेल्टा करता तो ये इक्वलिटी आता ना। यहाँ पर क्या है डेल्टा की डेफिनेशन? व्हाट इज द डेफिनेशन ऑफ डेल्टा?
इन्फिमम ऑफ एक्स माइनस
इनफीमम
जेड।
मोड। सो इन डेल्टा सबसे छोटा है, ठीक है। अब ये जो
यस सर।
ये समवेयर यहाँ पर है, कहीं पर है, एम के अंदर कहीं पर है, हमको नहीं पता कहाँ पर है, लेकिन ये एम का
यस सर।
वेक्टर है, ठीक है। अब इधर से इधर की डिस्टेंस जो है ये डेल्टा से या तो डेल्टा के बराबर होगी या बड़ी होगी,
हाँ।
बाय द
यस।
डेफिनेशन ऑफ डिस्टेंस, ठीक है।
यस। यस सर,
इज
समझा।
इट ओके? So
यस सर।
from here you have 2 delta square. So, and see here this is greater than equal to, when you uh, take negative of this, the greater than sign will change and it will be less than equal to. So see here, this is negative, so it will be 2 delta square. Okay, any doubt? Hello, is it okay? Hello.
हेलो।
यस सर।
यस सर।
हाँ, आप बीच
हाँ,
में बोल
आप
देखो, जब मैं
बीच
पूछ रहा
में
हूँ
बोल
कि
देखो, जब मैं पूछ रहा हूँ कि
ये सही है तो
ये
आप
सही
लोग
है
हाँ या ना में
तो आप
आंसर
लोग
दो,
हाँ या
हैं?
ना में आंसर दो, है?
ओके सर।
Okay,
ओके सर।
this implies this Zn Cauchy sequence. Okay, why? Because this delta and delta m, they both converges to delta. So as nm goes to infinity, this portion will go to 0. Therefore Zn is Cauchy sequence. But we know m is complete. Okay, therefore it is convergent. So it will converge to somewhere. Okay, Cauchy sequence. And we also know that delta n goes to delta m is complete. Okay, this means Zn, this means Zn is convergent in M. So Zn converges to some point. So I am writing it Z. Okay. So for the moment I am writing it as Z. Zn converges to Z. Okay. And this Z belongs to M because M is complete. So the limit will be in M. So from here what we get, so since this Z belongs to M, X minus Z is greater than or equal to delta. But you also know that X minus Z, this is less than equal to, okay. So do this thing, X subtract and add Zn minus Z. So it will, wait for a minute. So this is equal to, and now take less than equal to X minus Zn plus Zn minus Z. So this part X minus Zn is equal to delta n. This part is equal to delta n, and converges to 0. Zn Zn minus Z. This is norm Zn minus Z, and it, so this part, this goes to 0, and this goes to delta. So this goes to delta. Correct? From here, so norm X minus Z is less than equal to delta. So here you are getting norm X minus Z is greater than equal to delta. Here you are getting X minus Z is less than equal to delta. Both implies X minus Z equal to delta. Do you see this? Is it okay?
Yes,
So
sir.
uniqueness part is easy. So I'll leave this for you. So what you do, you will assume that there exist 2 points for which, so you will assume that there exists a point Z and another point Z naught. Okay. So this is equal to delta and X minus, so for 2 point Z and Z naught, the distance is delta. Then you will prove that in fact Z equal to Z naught. Okay. So I leave this for you. Please do it your own. So you know how you will prove this. So when you say Z equal to Z naught, this means if you prove Z minus Z naught equal to 0, then you are done. So this means if you prove norm Z minus Z naught equal to 0, then you are done. So use parallelogram law to prove this. Okay, next theorem. It is a lemma. So if you see the statement here, M is a convex closed subset of X. So what if we take it a complete subspace? Okay, subspace will always be convex. Okay, so let us replace this by complete subspace. Okay, then see what we get. So the theorem is, so lemma says that in the last theorem, in the above theorem, let M be a complete subspace of X. okay, and some x is fixed. Then here you will get that that y is, okay, uh, then y equal to let me, okay, here, so do one thing, uh, so here what we have written, then for given x there exists a unique y such that delta equal to norm x minus y. So so since I have written here this unique point as y, so you may replace at this place Zn convert, so rename this Z by Y, so you will get Y here. Okay. So everything goes fine except we are renaming it, and this we are doing because in the proof, sorry, in the statement of the theorem, uh, we are writing that there exists a unique y in M. Okay, nothing goes wrong here. Only thing we are renaming the vector. So then here also we will use y only. So then this vector x minus y is orthogonal to y. So let us see what this theorem say. Okay. Okay. So let us see. We are assume we are in R2. R2 is simplest case. Okay. So a complete subspace y of x. So in R2 the subspace is complete. So this is the subspace. Let us take this as a subspace. This is our y. Say this is y. Okay. And we are taking any point x here. So this is x in R2. Okay, so what does this theorem say? So this theorem says for this y, okay, we will get, so from above theorem we will get a y in y such that norm x minus y is the distance from x to capital Y, subspace y, and you all know what is that distance. So from your coordinate geometry, so distance of a line from a point is, please tell me, कोई एक बताइए कि एक हमें लाइन गिवन है और एक पॉइंट गिवन है बाहर, लाइन के बाहर, तो लाइन पॉइंट से लाइन की जो दूरी होती है कैसे आप फाइंड करते हैं, कैसे पता करते हैं?
Sir, y minus y1 is equal to mx minus x.
y माइनस, नहीं मैंने आपसे इक्वेशन नहीं पूछा है, मैंने पूछा आपको एक लाइन गिवन है, लाइन का इक्वेशन आपको पता है जो भी है, ठीक है, बाहर एक पॉइंट है, हाँ,
तो d is equal mod p is equal to d ax1 plus by1 plus c upon a1 square b1 square c1 square.
ये आप फॉर्मूला बता रहे हैं, असल में होता क्या, मतलब वो क्या रिप्रेजेंट करता है, परपेंडिकुलर रिप्रेजेंट, हाँ, तो ये x से y में आप परपेंडिकुलर डालते हैं, ठीक है,
हाँ वही डिस्टेंस होती है वो,
तो ये हमें मिली y। अब ये जो थ्योरम कह रही है यहाँ पर, ये कह रहा है इन द अबव थ्योरम लेट m बी कंप्लीट सबस्पेस y ऑफ x एंड x is fixed then x minus y is orthogonal to y। Okay, so orthogonal to y means it is perpendicular to this subspace. Okay, so this is 90 degree. This is what this theorem says. So ऊपर वाली थ्योरम ऐसा नहीं कह रही थी. ऐसा क्यों नहीं कह रही थी, उसका कारण देखते हैं. फिर से उसका कारण देख लेते हैं एक बार. So again we are in R2. Okay, and suppose this is the set, convex set. Okay, and assume that this is complete. So endpoints are there. Okay, so this is not a subspace, this is a set. Now take a point somewhere here. So this is your point x. Okay, what will be its distance from this set? It will be this thing. So this is your point. It will be distance of it will be length of this vector, correct? Do you see? And you know this vector is not perpendicular to this set. Okay, let's prove this theorem.
Let's prove this theorem. हाँ.
किसी ने कुछ बोला?
किसी ने कुछ बोला?
Okay, नहीं बोला तो पढ़ते हैं.
नहीं बोला तो पढ़ते हैं.
So let's prove this.
Let's prove this.
So first set that z equal to
First set that z equal to set
equal to x minus y,
equal to x minus.
and assume z is not perpendicular to y, means this is not true. So if this is not true, by definition, this means there exists a vector y in y, okay, such that this inner product is non-zero, correct? So this gives some an scalar, call that scalar beta, and since this is non-zero, y1 is non-zero. Clearly y1 is non-zero. Otherwise, if y1 is 0, then
y1 is 0, then
this inner product would be 0. Okay. Now, for any scalar, assume this thing. Furthermore, for any scalar, alpha in k from z minus alpha y square, and you compute this. Okay, so by definition, norm z minus alpha y1 is same as this thing, and I will omit some part of calculation and I will just write choose alpha bar equal to beta bar by norm y1 square. Okay, choose this thing. So this will give you beta bar minus norm y1 square alpha bar equal to 0. Okay, and then what you do, you use above theorem, this theorem, okay, and you know norm of x minus y is delta. This is the distance of the subspace from the point x. So this means norm x minus y, so nothing but norm z, this is delta. And use this, use all these things, and you will find, if you calculate this portion using alpha bar is this and norm x minus y is this, what you will get is less than delta square. But this is not possible, so you have to show why this is not possible and get a contradiction. Okay, so this is an exercise for you, so I will not complete the proof here. So here, using this, you get a contradiction, but you are getting a contradiction because you assume a wrong thing. You assume that z is not perpendicular to y, so therefore your assumption is wrong and z is perpendicular to y. Okay, now let me define another notion, that is called direct sum. If you remember, uh, uh, last lecture, so what we did there, so for given subspace E, which is proper subspace, you find its EPERP, okay, orthogonal complement. So if this is E, then this is EPERP. And if you remember there, what I said, that EPERP and E both spans the whole space. Okay, so this gives the notion of direct sum. So let's see what is this, and you have already seen this notion, this concept in your linear algebra course. Okay, vector space X is said to be the sum of two subspaces Y and Z. These are subspaces of X if every element, each vector in capital X can be uniquely expressed, neatly expressed okay, can be uniquely expressed as x equal to y plus z, okay, where this y comes from capital Y and the vector z comes from capital Z. If this happens, then we write and we repeat x equal to y direction z. Okay. So in the last lecture, what I said that E and E per spans X, the whole space. This means this suggests that whether X can be written as a direct sum of E and E per, and in fact this is true. So let's prove this. Let's prove this theorem. Suppose we have a Hilbert space, so this is true in complete inner product space. So let Y be a subspace of a Hilbert space say H if Y is closed, okay, then H equal to Y direct sum Y per. Let's prove this theorem. So if you see what we have so far, so here in this theorem we have shown that we have a complete convex subset of X. There exists a unique Y which gives the distance. And in the second theorem, in the second result, if that set is complete subspace of Y, then this vector X minus Y is orthogonal to Y. So we will use these things. So here H is complete and Y is closed. H is complete, Y is closed. This implies Y is complete. Okay. And since Y is a subspace, so it is clearly convex. How? So since Y is subspace, it is convex. To see this, it is very easy. So this means for any two vector X and Y, in Y you have to prove that lambda X plus 1 minus lambda Y, this belongs to Y. See here, this, if X belongs to Y and Y is a subspace, lambda X belongs to Y. Similarly, 1 minus lambda Y belongs to Y. So these are two vectors in Y. Y is a vector space, sum of their, so their sum is again a vector in Y. Hence Y is convex. Okay, this was easy to see. Now, okay, so what happened here? So now what we do, okay, here, how we use this theorem. So far what we get a convex complete subset of X, that is Y. Capital Y is convex complete subset of X. Then it says that we will get a unique element, unique vector in Y such that this gives the distance. Okay. So from above two results, so first one gives the unique point, second one gives that actually this vector X minus Y is orthogonal to Y. Okay. So from above results, this this theorem is asked in your examination, you have to prove this lemma and that theorem as well. Okay. So from above result, so let me correct myself. If you if you are asked to prove this theorem, then I said you have to prove this lemma and that theorem. It is correct if it is correct when you are using this method. There might be another method where we will not use these two results. You can give any other proof as well. Okay, if you know. Otherwise, if you are using this method, then please uh, uh, give complete details. Okay, from above results, what you get, there exists y in capital Y such that z equal to x minus y. So this is the vector and this is perpendicular to y. Okay. So from here you will get y equal to x plus z. So see here, uh, see here this x is an so this x was an arbitrary element. Okay. Okay, let me write. I have not written the complete sentence. I let me write it first. So I should have written this thing. So from above results, above two results, for every x in x, now it is complete. There exists y in y such that z equal to x and uh, and uh, z is perpendicular to y. Okay. Now this x was arbitrary, and you see x can be written in this form, y plus z. Yet this y comes from y and this z comes from y perp. Okay. So what we have shown that any arbitrary point can be written in this form, x equal to y plus z. But what we have not yet proven is this is unique. This expression is unique. So if we prove that this expression is unique, then we can say that x is a direct sum of y and y perp. Okay, let's see uniqueness. Uniqueness part is easy. So what you do, you take, suppose there are two representations. Suppose x can be represented at y as y plus z, and x can be represented as y1 plus z1. So both y and y1 belongs to y, both z and z1 belong to y perp. Okay. So suppose this is true. So since y and y1 both belongs to y, this means y minus y1 belongs to y. Similarly, y perp is subspace. z minus z1 belongs to y per. Now use this equality. So here y plus z equal to x and x equal to y1 plus z1. So this means y plus z, this means y plus z is same as y1 plus z1. From here, this is nothing but y minus y1 equal to z1 minus z. Okay, so z and z1 both are vectors in y per, therefore z1 minus z is also an element of y per. Correct? But you know y intersection y per is always, please tell me what is y intersection y per?
y intersection y per?
Phi.
Phi.
No, it's not correct.
No, it's not correct.
See this
No.
figure from here, please observe it and
Observe it
Zero,
and,
and tell me it is
tell me it is
0 sir.
0. बहुत बढ़िया. So y intersection y per is 0. So these two elements, so therefore this vector, so since this is same vector, z minus z1, it belongs to y per and it also belongs to y. So this means it would be, so this means y1 minus y1 and z1 minus z, this is equal to 0. Any doubt? Hello?
Yes, sir.
हाँ, डाउट है आपको?
डाउट है आपको?
No, sir. आगे
0 के इक्वल कैसे लिखेंगे?
अच्छा, 0 के इक्वल कैसे आए ये समझ में नहीं आया आपको. ओके, ये एलिमेंट, ये जो वेक्टर है y माइनस y1 कहाँ पर है?
y में.
y में. और जो दूसरा वेक्टर है z1 माइनस z, वो कहाँ है?
y पर में.
तो ये वेक्टर था y परप में, और ये वेक्टर किसके बराबर है?
सर वो y
y
के
माइनस
कैपिटल
y1 के. और ये वेक्टर कहाँ पर है? y में. तो इसका मतलब ये दोनों वेक्टर इंटरसेक्शन में है, मींस जो भी है वो दोनों सेम है, सो ये इंटरसेक्शन में है. करेक्ट?
यस सर.
बट यू नो इंटरसेक्शन इज 0. दिस मीन्स y minus y1 equal to z1 minus z equal to 0. From here you will get y equal to y1 and z1 equal to z1, and uniqueness follows from this. Okay, so what you have proven is any arbitrary element of any arbitrary vector of x can be represented as sum of two vectors from so sum of vectors from y and from y perp, and in fact this expression is unique, this sum is unique, therefore x is y, y direct sum y perp. Okay, correct? Oh, it's almost time, so we will do it next time. So I'll give you an exercise. So problem, let A be a convex subset of a Hilbert space and let Xn be a sequence in A such that limit n goes to infinity, norm Xn equal to D, which is infimum, is so that Xn convergent. Okay, so here it is given that H is Hilbert space, means it is complete. So use completeness somehow. So Xn is convergent, means convergent in X. So prove that Xn is Cauchy and use. So prove that Xn is Cauchy in H. Okay. So if Xn is Cauchy, it will definitely converge. So this is a hint for this problem. Now there is another result that you will prove your own theorem. But it says we have a inner product space X and inner product space, and we have a non-empty complete proper subspace of X. Complete proper subspace of X. Then ampere is non-empty. In fact, this is non-zero. So two things you have to prove: this is non-empty, and in fact this is non-zero. This subspace is not equal to 0. Okay. So some part of this we have already shown. When it was complete subspace of X, we have shown that whatever we have shown, you know. Here we have shown something. It was when it is complete subspace, then it was orthogonal. So you have to show that this vector is non-zero. Okay. So I will stop here. Any question, comment, doubt, please ask. Hello. Okay, if there is no question, no doubt,
If there is no question, no doubt,
then I will stop here.
then I'll stop here.